Hello again, and welcome to today's webinar on EOS and ESD. My name is Ed Dodd, and I'll be your host. Today's presenters bring a wealth of experience to this topic. Greg Caswell, Senior Member of Technical Staff at DFR Solutions, has spent decades working with the electronics industry on design and manufacturing issues ranging from component packaging to system assembly. He literally wrote the first book on SMT, and he's worked deeply on ESD and EOS issues during design, manufacturing, and analysis. He'll be joined today by Jeff Donohue, founder of Pragma Design. Jeff has presented at IEEE EMC, ESDA, ISTFA, and has recently co-authored a new textbook with other ESD experts on ESD co-design fundamentals. He's also been a contributor to industry groups and standards bodies, including IEEE 802.11, the ESD Industry Council, and has served in working groups and on the board of directors of the ESD Association. So with that, Greg, I'll hand it off to you for start.
All right. Thanks, Ed. Good afternoon, everyone. As Ed mentioned, we're going to talk today for the next hour about understanding and mitigating EOS and ESD in electronics. This is the abstract that we posted. Essentially, ESD is the sudden flow of electricity between a conductive and non-conductive surfaces that builds a charge and then discharges it to ground, and that can impact any susceptible electronics in its path. We've all walked across the carpet and grabbed a doorknob at some time in our life, and that ranges from 5,000 to 15,000 volts depending upon the humidity, and usually that's well above the threshold for most electronic devices, yet doesn't hurt you. Conversely, EOS failures are typically due to a surge or overload on the circuitry. They exhibit much more damage due to the level of current and voltage involved, and what we're going to try to do today is walk you through some of the different failure modes, provide insight into what you need to do to protect your circuitry and deliver a reliable product so that ESD or EOS are not an issue. There are three dominant ESD models for ICs: the human body model, the charge device model, or the machine model, and then there are others at the system level. The human metal model of IEC 61000-4-2 or ISO 10605, for example, and you need to make sure that you don't get confused by those because they address totally different elements of ESD protection. So looking at those models, the human body model simulates the event when a person is charged up either in a positive or a negative potential and then touches a device that is at another potential. The charge device model simulates the event where a device charges to a certain potential and then gets into contact with a conductive surface at a different potential. And the machine model simulates the event when a part of the equipment or tool comes in contact with a device at a different potential. The human body and charge device models, human body model and charge device models are considered to be repeatable or real-world models, but the machine model is deprecated. So, because of what we do to ourselves in our designs and reducing the size of IC features and continued miniaturization, we've made things with respect to ESD susceptibility worse. As these feature sizes continue to get smaller, device robustness diminishes, and typical system level stresses can be 8 kilovolts, 30 amps, and maybe as many as 200 plus ESD events. Testing well powered can increase the damage susceptibility, and that could be as much as 50% in some applications. This slide gives you a nice image that shows the difference between a 2000 volt human body model, which is the gold trace at the bottom of the figure, versus a IEC 61000-4-2 8000 volt level 4 ESD event. And you can see there's considerably more energy involved in the system level activity. Portable environment electronics increase these threats. It can be a lifetime product liability due to latent type defects, and requires a significant effort on your part as the designer to look at ways to mitigate ESD at the component, package, and board and system level. So these are some of the things involved with the scaling that's been going on. We have smaller IC geometries. Companies are now making parts with gate geometries down around 14 nanometers or even some smaller. We're doing things at higher frequencies, a lot more signal line capabilities, keep making things smaller, so we have reduced board space. And so that means that we have reduced budgets for ESD protection at all levels, both the chip and on the board and for the system. So, every one of these scaling effects, the IC technology advances has had a mostly negative impact on ESD. Today's ICs can no longer provide adequate protection by themselves. And then new circuit features, RF applications, they're increasing the complexity to both ESD and system level IEC protection. So what do you need to do? So you need to provide protection at the IC, the component package, and the system level. And in those cases, different approaches are required to achieve reliable protection. There are different technologies available to assure reliable ESD protected product at the device level, at the package level, and at the system level. And there are testing methodologies available to ascertain the true protection level that you have. These can be capacitive discharge or transmission line pulsar type systems. So what are the kind of failure mechanisms? So ESD is when objects moving with respect to each other transfer a charge. So the amount of the charge depends on the materials involved, the speed, and how close these materials are to each other. And then their dissipation depends on the conduction paths involved. You can get extremely large voltages. The drier the environment, the worse the probability of some sort of an ESD event. Their materials have easily stripped electrons. They're more susceptible. And if there is no imminent discharge path, that also presents a problem. Like I mentioned earlier, the human perception for an ESD type activity is around 5,000 volts. At that point, many components or circuits are long since destroyed. If you look at some of the failure mechanisms, electric field induced failures would be one approach. This breaks down the gate oxide of a device and shorts the gate permanently. Potentially fields could push carriers into insulators. That may just degrade performance, but eventually that latent type failure could manifest itself as a completely defective device. Thermal destruction, another mechanism. That's where you might see a resistance in a path that's subject to local intense heating. That could be either contacts, vias, junctions. And typically what we see is the weakest link goes first. And you'll also hear us talking today a lot about latent failures or walking wounded. These types of devices have been hit by an ESD pulse. They get increased leakage current, possibly an increased resistance path. The junctions are softened as a result of that, and the latent damage will accumulate without any kind of external failure signature until the device goes from walking wounded status to full failure status. So, things that you can look at from a design guidelines perspective, things to be careful about. You have to look at how heat travels, for example, with silicon and silicon dioxide. There's about a 10x difference in thermal conductivity between those materials. Aluminum melts at a much lower temperature than silicon. You need to be aware of that. Uniform layout is crucial. So you try to avoid current crowding situations in your design, eliminate snaking gates, look at the spacing of contacts from junction edges. It's Craig again. Look at guard rings and things of that nature to improve performance. Here's some examples of failure mechanisms, some photos to show what an ESD impact can do to the surface of a device. You can see it can do small punctures. It can damage metal lines. It can have an impact on the gate or drain elements of a device, and cause the failure that way. The reason that we're giving you these to look at is because they will contrast nicely with EOS type damage. So you want to pick this one up, Jeff?
Yeah, thanks. This is a kind of a busy slide, but it talks about how where we induce some of these ESD and EOS entry vectors into the product at the chip level at the top, and then as you go down past the dotted line into the system level, putting it on a circuit board, then putting the circuit board in a enclosure, and then shipping it out to the field. And as you go down this chart, when you have the ESD failure, its impact is much more expensive as far as what's damaged and the cost to remediate it. So on the right side, we have at the beginning HBM and CDM chip level type ESD events, and if that causes a failure, that can be detected in the device test before it's shipped out. Again, IEC system level and charge board event strikes can be caught at their level. But on the left, we're talking about the walking wounded again. What happens if you get a latent damage event? It can go into the chip device but not be recognized at chip test, and may not show up until system level test, or may not even show up until an eventual field failure. So this is the kind of a continuum of entry vectors and what can happen with the varying amount of detectability of the fails. We go to the next slide. We've got some more pictures, and the question becomes, during a failure analysis, who's really at fault? As far as you see the ESD failure there, but was that caused at the chip level, or during system integration, or in the field? And was it a latent failure that was exacerbated at a later time to become a visible ESD failure? So the next issue on the failure analysis on the next slide is actually from a NXP research paper that showed a common problem called that filaments are grown within junctions and devices such as ESD clamps, where there is nonlinear concentration of current flows in a junction or in the substrate that create these micro annealing, or these little filaments that grow, and they will not demonstrate any visible or electrical failure signatures until they grow far enough to puncture the junction. And at that point, they short out the junction. So this is an example of a walking wounded, where it's getting worse and the structure is degrading, but you can't see it yet. So I guess you want to take back, Greg? Or?
All right. So some things to think about with respect to design practices for ESD. We'll talk a little bit about more of it, but use the ESD Industry Council SEED method to help you out. Looking at system efficient ESD design, consider the potential residual ESD paths throughout the system. Identify all ESD sensitive parts on the drawings. mark locations of them on the board with the ESD symbol if there's room, and consider the entire system design as ESD sensitive or having a susceptibility at some level, and then providing proper identification of target levels is required. So if we look at that and say, okay, use ESD protection on all susceptible parts, at the box or system, you can have an ESD rating that's, say, greater than class 2, which is 4,000. You might have internal components that are not exposed to outside connectors, and you have ratings for those. If you have high-speed RF or gallium arsenide parts, they are particularly sensitive to ESD. Gas parts are typically rated as either class 0, meaning they're susceptible up to 200, that they're capable of to about 250 volts, or they might be class 1A, which is 500. So they're very sensitive, and only the best protection designs and handling procedures will prevent damage to those types of parts. Place ESD-sensitive parts and traces to avoid locations where the board might be handled. Consider ESD as well as RF shielding, and make sure that you install protective devices before ESD-sensitive parts, and avoid coupled ESD events. Do not route traces to ESD-sensitive parts near lines connected to the outside world. Perform circuit analysis to ensure effectiveness of ESD protection. Test boards and systems for internal and I/O ESD tolerance, and make sure that your protection devices, they must be connected to a good solid ground connection to accommodate up to 30 amps of ESD spiking. Jeff?
Yeah. So this is the concept of the current entry vector of an ESD pulse. We have a connector on the left here and a TVS compressor device next to that. It's good practice, and then we're trying to protect an ASIC that also has a clamp in it. The common misconception is that the TVS protects the system and that's all there is to it, but really it's just a simple KCL current division between the TVS and the ESD clamp in the ASIC or the device to be protected. So first order analysis is we put an inductive current probe on the trace between the TVS and the ASIC and look at the current through that. We call that the residual pulse. Second order analysis that is presently defined as a new standard for a standard practice for ESD scanning is to take and look at a probe that goes across the system and actually sees the pulse as the H field changes and the current flows through the circuit board. And you can see here in this example, there's the red circle is where there's a TVS device on a USB port, and the yellow line is the residual current pulse along the DC port trace and going into the ASIC there at the right. And what this shows you is the divergence that we think of the protected system as a schematic, but really these elements that are nearby are being coupled with the ESD residual pulse. That's like in the blue circles there. So it's not as simple as you zap it and you're protecting the circuits that you think you're protecting, but are you protecting the ones that's nearby the ones you're protecting? You go to the next one. That's susceptibility scanning is the inverse of current reconstruction like that, where we have the system running and we scan the probe over the system and inject various levels of ESD-like EMI so that it resembles what an ESD discharge nearby would be. We have phones on the market now that if you discharge an ESD gun on the table near them, not even to them, that it can upset them. And so the idea is to find out where are the hot spots within that system and which chips are getting upset or which chips are the entry vector for that. So that's the susceptibility scanning. And then on the next page, we go back to current reconstruction. Again, this is actually the same plot we showed, but it's two different populations of the board, where the top plot has no TVS device on the left side there, and you can see a large residual current pulse during the strike going into the ASIC. And then on the bottom there, where we have a TVS device on this USB port, the top left, that is clamping a lot of current to ground during the pulse, and you get a much smaller residual pulse going into the device. So the key here was that in between those 2 points, there was a Ethernet port that was coupling energy into the Ethernet MAC, and that upset the Ethernet MAC, so that when you strike the USB port, it would upset the Ethernet state machine. And the more USB protection you put on for bigger TVS, etc., the worse you made the problem, because you were clamping energy near that Ethernet port. So that's the kind of thing that you can find when you're doing the scanning, because it actually listens to the machine rather than estimating what you're doing in a schematic type mentality. You look at the next one, is about failure criteria. So we have, when we have functional changes for upsetting the system and either hang or corrupting the display or things like that, those are soft errors. But when we have hard errors, sometimes it's not as simple as seeing a big hole on the silicon later on where ESD damage is visible, but it could be something between a latent and a physical visible damage, where the leakage is not apparent at DC, but it may be apparent in high frequency domains, such as this differential link here, as the device was struck with about 20 strikes of system level ESD. While it's running, the transmitter output eye diagram started to collapse as the leakage within the device at high frequencies dropped, but it was still not visible damage. So you have to set your failure criteria. What are you trying to call a failure, so that you know, if I strike it with 8 kV, it may die, but if I strike it with 5 kV 50 times, it may be a walking wounded, as we were mentioning. So I guess the final slot here for these type analyses, next slide, is an example of a relative susceptibility between two chips, because you want to kind of characterize if you've got two devices, or one with protection or with a different type of protection, and you want to see what the susceptibility is. This kind of scanning gives you a map that on the left side, the only area that can be upset is near the JTAG pins, which, you know, if you get enough energy into those, then you can glitch it into a test mode and upset the operation of the chip. Whereas on the right side, with this newer chip, external pins that go to, I think this was a display port to VGA converter, are also very susceptible, meaning that a strike on or near the pins could hurt it, and it's clearly from A to B, the one on the right is far more susceptible to ESD pulses. And you can make your choice on vendors and protection strategies based on these kind of scans. So I kick it back to you, Greg.
Okay. You know, if we look at things from a pin sensitivity perspective, that can be any pin of a discrete ESD sensitive part. It might be a FET transistor. Yeah, it might need protection if it's not directly connected to a power supply. Input pins because they have little or no built-in ESD protection, are vulnerable, more so on high-speed devices like gallium arsenide. Pins other than inputs can also be sensitive because an ESD pulse can affect the internal voltage levels, and any improperly terminated or unprotected pin can be a conduit for ESD. Supply pins, they provide a reference bias connection. They shouldn't need additional protection as long as they remain connected to the power supply. And outputs of logical or functional parts designed with active, usually buffered output stages, may have a clamping diode protection scheme to the supplies, and may also not need additional protection. You have to check with the ESD rating of the part. If ESD-sensitive parts are used, then the circuitry connected to the device pins needs to be evaluated. Ensure that it provides attenuation to prevent voltage in excess of the part's ESD ratings, in case the pin or connected traces are contacted during board assembly or handling. Often the recommended circuit components for operation of the part will provide adequate ESD protection, and you need to verify them by either analysis or simulation or possibly testing, and we've provided some assumptions for that analysis here. Jeff?
Yeah, so with the this is an example of the system-efficient ESD design simulation, and the key here is to get an accurate model in the ESD regime for the DUT or the TBS or the device under protection, the ASIC, so that the models that you might get for signal integrity, which you could simulate and do this kind of current division analysis, are usually only good for a few milliamps above the rails, because they do model the ESD clamps within the device, but they only do it for overshoot and undershoot, really. And when you get an ESD simulation, you're dumping 15, 20, 30 amps into the circuit at extremely high edge rates. You need to have models that go out that far. And what will happen is an interaction that can only, cannot be analyzed from just looking at the data sheet when you have two of them together, because if the device under protection has a clamp, turn-on voltage, and dynamic resistance lower than the TVS, then you may get a condition where the ASIC tries to turn on and protect and destroys itself before the TVS device even turns on to begin with. And that doesn't really help you. So that's what our the Pesto online simulation tool does, is a library of these kind of models and allows you to check all those and see which device protects your particular ASIC better. And we got some, next slide shows some different ways to roll your own models as well.
Okay, these could be passive networks that might be simplistic capacitors to provide protection, might be bandpass filters for slower devices, could be Schottky diodes or clamping arrays, and for higher speed devices it might be low capacity protection diodes, very low picofarad level capacitance, or it could be polymer ESD protection devices. So if we look at a simple capacitive protection scheme that's shown here, you want to make sure that the capacitance in this circuit, C2, is significantly larger than the human body model capacitance of 150 puff to minimize developed voltage. So you want to make sure that you can add a resistor if you want to bleed off the charge from C2, and then use a 200 volt rated cap. And this would be a simple circuit to help. If you go to bandpass filters for different higher frequency applications, they can be effective for RF. It's a good circuit, good protection. And this is just an example of a bandpass filter circuit for 850 to 2 gigahertz. Clamping diodes. This example shows the clamping diodes on a protected output of a device, and that the ESD at the output is clamped at approximately 14 volts with a 4,000 volt ESD hit through a 330 ohm resistance. So again, good clamping protection. Or you can have a polymer ESD plus an inductor circuit. The inductor shunts lower frequency energy to ground, removing stress from the PESD device. This kind of a circuit provides better protection than the PESD by itself, but it can be used alone for a wider bandwidth type operation. So, kind of to summarize this part of things, the design ESD protection for external system IOs to IEC HBM class 2, which is 4,000 volts, 150 PUF, 330 ohms. And you can do that for RF or signal inputs, control, and system IOs that do not have built-in protection. You want to design ESD protection for internal ESD parts, ESD sensitive parts to meet ANSI 2020, class 2 for 2,000 volts. Clearly you have to know the ESD rating of every part in your system, and parts rated less than class 2 should have additional protection added to protect the board during handling. For external system inputs, you can use bandpass filters or PESDs plus an inductor. For internal ESD sensitive pins, you can use bypass caps, a filter, or PESDs. Any pin of an ESD sensitive part may be at risk if it is not connected to a plane, a supply power point, adequately decoupled to ground, or protected by a filter. External IOs use low capacitance clamping diodes, as we showed, and PESDs if required to deal with speed issues. So trying to distinguish between ESD and EOS can be difficult. ESD damage, like we've shown in pictures, is typically small failure sites, not always visible without deprocessing the component. Usually no visible damage at the package level, whereas with EOS, there's much larger areas of damage, might be burned or melted aluminum or silicon in metallization, sometimes visible to the external portion of the package. So, EOS, kind of looking again, it's a thermal overstress to a component circuitry. You can have short pulse width failures, which are kind of like junction spiking, long pulse width failures, where you might end up with melted metallization and open bond wires. And then junction spiking can occur when the amount of aluminum migration into the silicon substrate has reached the point where the aluminum has penetrated deep enough to short a PN junction in its path. By that time, an aluminum spike is said to have shorted the junction, damaging the device permanently. Jeff?
Yeah, so this is a chart from the about a week ago, the release of the white paper 4 from the Industry Council. That is 189 pages about EOS causes, effects, and industry analyses all combined in one. And the big takeaway, the difference between EOS and ESD is that ESD is almost entirely a electrostatic charge that is stored in a capacitance, whether it be the human body effective capacitance or some board or chip level parasitic capacitance between a reference plane. So it's a limited, finite amount of charge that is dumped through a network, resistor and inductive network, to make a pulse that has a finite energy content, whereas EOS is a level of energy that is continuous often and can just go through and continue to exceed levels and is never dissipated by the damage it's causing. So EOS and ESD are not alternative. They are actually sometimes causal, in that an ESD pulse, for example, could turn on an ESD clamp, and maybe just like with ESD-induced latch-up, you can have an ESD-induced EOS event where the TVS turns on, it dumps a power supply rail, and that power supply rail ends up burning up the chip. You know, go to the next one. We can talk about more of the definitions from it. This is a huge kind of a NDF black box that many failure analyses are returned as EOS, where there's a very difficult to discern, as shown before, how much EOS and ESD caused EOS are not necessarily preventable by raising your ESD robustness. And in fact, there's no type of ESD protection that can prevent an EOS stressed pulse being applied and destroying the system. So, in fact, sometimes when you make the ESD clamp harder, you get worse EOS damage. So, the definition of EOS is exceeding the voltage, current, or power into the device and having that cause instant damage or a latent, undetectable degradation in reliability lifetime. So if you go forward one more, this is one of the historical definitions from actually the 20s and 30s during tube types circuitry that was defined as overload being something that exceeds a input specification or output specification for a system that would cause an unexpected output or an undesirable output. And so from that, the overload capacity and overload levels were discussed as these are limits at which you should not go past in order for the thing to work. And that, you go to the next one, kind of folds into their, kind of gives a very good graphical description of where the absolute maximum ratings, the AMRs, on the red side, and the maximum operating conditions are on the left side. In the green, as long as you're in there, there's no possibility of permanent or latent damage. And in region B, you're exceeding the maximum operating condition, which is, say, 10% over VCC, that kind of thing. You can exceed that for short periods of time and not damage the part either latent or immediately. But when you exceed the AMR, essentially this is the here be dragons on the map. And beyond this phase, when you exceed the AMRs, whether it be storage temperature or voltages and currents, you can get a little bit past that, and you have now violated the spec to say, at this point, the device is no longer guaranteed to live up to any of the electrical specifications or reliability specifications. And even though you can see that the probability of immediate damage may still be 0% for a while in region C, until you finally get to such a huge EOS event that you absolutely are guaranteed to blow the thing. So I guess go to the next one is that the key thing is that the AMR has to be set by the chip manufacturer, and it's not necessarily a test value. There is some guard band between that AMR and where they know the destruction will absolutely begin, and therefore you shouldn't design to ever try to be in region C, which is because you're probably inducing some kind of latent damage. And at any rate, the real AMR acceptance is a negotiation between the vendor and the buyer, and you've got to make sure that, as we showed with that comparison with susceptible parts, that this is something that will fit your application. And this is also critical when you come back and you're doing a failure analysis to break it out. What was the source of EOS? So I guess, Greg, you want to take back, or we do the?
Sure. Yeah. So, sources of EOS. EOS is, like we say, usually assigned any visible damage signature that appears to have been the result of excessive voltage or current. The damage could be a violation of an AMR caused by incorrect biasing. Could be an over voltage, maybe induced latch-up conditions, extreme uncontrolled ESD, misorientation of a component or something else in that vein. And the damage may also have been due to a defect in an individual weak device, an improperly set AMR, or an intrinsic weakness in a technology. So, a couple more definitions. Electrically induced physical damage, or EIPD. And this is damage to an integrated circuit due to electrical thermostress beyond the level which the materials could sustain. This could include melting of silicon, fusing of metal interconnects, thermal damage to packaged material, bond wires being fused, and other damage caused by excessive current or voltage. As compared to electrical overstress, and this is where a device suffers electrical overstress when a maximum limit for the voltage across or the current through or the power dissipated in the device is exceeded and causes immediate damage or malfunction, or a latent damage resulting in unpredictable reduction in its lifetime. So there are three main categories where EOS damage can occur: power handling, unpowered handling, switching, alternating current applications, and that leads into an approach that Jeff will talk to on this slide.
Yeah, and I think that's the key takeaway from the Industry Council white paper is the distinction between the induced physical damage and the concept of electrical overstress, and that EOS is an event and electrically induced physical damage is a result. So the crater is the EIPD, and the meteor before it hits is the EOS. That's the event. So in this chart, which is called the fishbone, you've got three main areas that we went over, which are powered handling, which is hot plugging, and anything that occurs while it's powered that can create EOS. Unpowered handling includes large, like charged board events that could make charged cables is another example you see there, and dropping it, mechanically damaging it, that then causes later on when you power it up to blow traces and things. And then switching, having to do with flyback, inductive switching and things like that. I think Greg has another slide in here about the ignition systems in trucks and things that cause stuff like that. You want to go to the next one. So I guess the issue is to understand the AMR, know where that line is that be dragons beyond this, the realistic specification and negotiations between the customer and the vendor to, these are the limits and don't do this. And then whether it's preventative or in a after-the-fact failure analysis, the accurate determination and the true root cause of the electrically induced physical damage is what you want to find to define the EOS or ESD or ESD-induced EOS. And this is very important in order to mitigate it on future designs, as well as to quickly resolve the root cause of existing problems. Let's see. Now the next slide is tools to help in all of this, including EOS and ESD. It grows out of a kind of synergy here with EMI and EMC testing, in that with RF scanning for immunity and EMC compliance scanning, you have the RF engineer and compliance engineer has a lot of tools in order to test their compliance with FCC requirements. However, there's never been a good debug tool or tool set available for ESD other than the ESD guns and or ESD pulse simulators to try to break the thing. So the new current reconstruction or current spreading, resonance scanning, and ESD susceptibility scanning now provide parallel type tools to easily find the hot spots and problem areas that can lead to root cause. So I guess you want to take back on the next one.
So, some things, what happens if you have a return exhibiting EOS damage? So to be able to figure out what happened, you have to have a requisite knowledge of the application at the time of the damage. And that might include where in the application did the damage occur, what were the environmental conditions at the time or during the test which revealed the damage. For example, in an automotive application, that would include the environment within the particular location of the car. You need to be able to look at the schematics, layout of the board, to be able to ascertain any potential issues. You need to understand the power supplies, the ground and input-output connections and voltages at the time of the damage, and details of the interconnection of the devices on the board. Anything else in the way of precursors to damage are also useful. Understanding maybe any kind of background on assembly yield, test issues, or previous device analyses indicating a weakness are also useful in helping to pin down the issue. If we look at transients, there are many ways that a transient can enter the system. Some may be from a directly applied source, and there are several different ways. You can get overvoltage spikes from the supplies, charging and discharging of large value capacitors directly into system pins. It could be a long charged cable connecting directly into system pins, or it might be a system being supplied with power before its connection to ground has been made. And it could also be due to inductive kicks or loads on a particular system. So things to look at, other ways, process-induced. These could be assembly or IC misprocessing resulting in a low breakdown or shorting. Might be a charged board. Jeff's mentioned that several times. And that sudden discharging of the board to a ground potential can result in a discharge pass through the board's supply and ground tracks, which then directly route to or through components, causing excessive current densities and potential damage. Test-induced is another area. You can have voltage transients resulting from incorrect power supply switching or incompatible switch control voltages. You might have glitches on supplies. and different types of, say for example, incoming testing using a charged multimeter. And then coupling of external radiated energy into unprotected devices of the system. This can occur when which generate or are in charge or in the range of this type of energy, which can also cause high voltages, currents that can cause this damage. So at other places, oscillation can cause EOS. Linear mode operation, shoot-through is one that we've seen quite often at DFR. Vendor quality, the selection of the components that you're using. Electrostatic coating that might take into consideration conformal coating, and that it does provide some benefit from ESD arcing. Outsourced processes, if you're a manufacturer and you don't have control of certain processes, then that's a potential source. And weaknesses in the board design, and we'll talk a little bit more about that in a moment. You have to, during an analysis, look at the identification of the damaged part. You have to look at to determine the reason for the non-working system. You need to identify that part and perform a detailed inspection of the system, the component, the board, and down to the IC level. There's a detailed description here of an example of an EIPD signature. We're going to kind of let you guys take a look at that later on and go through the calculations yourself. This is a chart that kind of gives some examples of where the different types of surge or stress comes into play, what the duration of the pulses are, and what the energy level in joules is with respect to each of them. We've also seen situations, for example, where the ignition of a heavy vehicle or truck, that can trigger a possible damaging effect to MOVs or capacitor combinations on that input that don't limit the voltage level sufficiently. Three things that you can, analysis steps that you can summarize here. What's happened? Describe the situation, understand it, complete failure analysis. How did it happen? Analyze the paths of the stress pulse and its electrical parameters. Look to replicate the EOS event if you can. And then, why has it happened? Get an understanding of how the stress aggressor, the victim, and the protection have interacted so that you can obviate these types of problems in future designs. This is a couple of examples from one component of two locations on the same device showing EOS damage. And if you compare that back to the images we showed earlier of ESD, then this is, you can see that it's much more significant damage. You can also get melting. You can see that on the left-hand edge of this pad in this diode. Significant damage again, likely due to EOS rather than ESD. One of the other areas that we find is critical at DFR is board spacings with respect to the voltage levels that will be applied to the board. This chart is right out of IPC 2221. It shows the minimum spacings required with respect to voltage between conductors for internal conductors, external uncoated with conformal coating conductors up to 10,000 feet. Above 10,000 feet, the numbers change dramatically. External conductors that are uncoated again, but above 10,000 feet. And then looking at the assembly, external conductors with and without conformal coating. And you can see that those spacings vary quite a bit. And you need to pay attention to those. For example, if you do have a couple of points that are too close together, and you're getting an ESD issue or an EOS issue because of that spacing, then you have two choices. You can either obviously widen the spacing to something that's going to behave, or maybe conformal coating is the answer. So this chart gives you that information to help you make that decision. So with that, Jeff and I will say thank you and open it up to any questions, Ed.
Great. It looks like at the moment we don't have any questions. Everybody, if you have anything, take a moment to look at the question section on that right-hand side panel. We'll give you, I guess, 1 or 2 minutes, because I know it does take some time. And if we don't have any questions at that point, I think we'll end it. And so, Greg, Jeff, is there anything maybe you didn't cover, or you wish you had spent a little more time while we're waiting for questions that you wanted to expand upon?
I think the only other thing we've got here is that there are some reference links that we've provided to the attendees so that they can do a little bit more digging on their own and get some useful information about ESD and EOS.
Yeah, the ESDAA, ESD Association has a really good 6-part series of introduction to facilities and system and chip level ESD fundamentals, and then the Industry Council White Paper 3 and White Paper 4. White Paper 3 is misconceptions and baseline analysis with seed for ESD and system and chip level, and then the White Paper 4 is a really comprehensive, kind of the first of the industry deep dive on EOS and how it's perceived throughout the industry as well. Plus, it's got a lot of neat case studies and ways to induce problems and blow chips up. So take a look at those.
All right, looks like we have a question. HDMI circuits have a protection device added. Can you comment on the effectiveness of those devices for those applications?
Okay, so I guess I'm not sure which part you're talking about, but there's an overcurrent protection device for the power supply out to drive the sink, I think, but probably you're talking about clamps within the ASIC. So again, that's typically an IC level clamp, and it's designed to protect the device for the HBM or CDM type pulses that you would see during the manufacturing. It is not anything that's rated like that does not protect you, as the Greg's first big slide showed you, against massive ESD pulses, or certainly a cable discharge event where you have you can actually get triboelectric charging within the differential pairs in the cable if it's loose, just by wiggling it. And some of those cables you can generate several hundred volts on the pins, and then when you plug that in, it's a direct discharge of that large capacitance in the cable into the device, and that can cause EOS as well. But you just need to run. That's what the seed analysis does. Is it you characterize the ASIC that you're trying to protect, and they all have some protection in them for, and then find out how much external protection you need to get to the system level target that you're trying to hit. I hope that made sense, or maybe.
So you're saying longer cables would be worse?
Yeah, well, there's not a present standard on charged cables. The ESDA actually does have a system level working group that's looking at that, and there's no common way or standard practice to test or characterize such a pulse. But yeah, the longer the cable is, you just think of it as a big box of packing peanuts. You know, you shake them around and you get high voltages. And then you have those two wires that are essentially make a big long capacitor, and the longer it is, the more capacitance it has. So it's a real big problem, and it's more common in Ethernet cables that just have open twisted pairs for very, very long distances. So.
I got another question here. Are flywheel diodes effective enough protection against EOS caused by inductive load surges?
I have to say I don't know what a flywheel diode is. Maybe it's we're using a different terminology, but maybe flyback, clamp snubbers or something like that. Yeah, again, I don't know, whatever it is, whether it's, passive devices like Greg had shown or any other kind of active device, you have to characterize that thing's IV curve and its response time, and you really have to simulate the things, because whatever the device you're trying to protect, if it has some IV response as well, and at some point on that curve, it's going to self-destruct. And you want to make sure that your external device is taking enough of that current and power and dissipating it during the pulse, so that those levels are never exceeded on either part to destruction. So whatever kind of protection it is, it's the same procedure to analyze.
All right, I think we have time for one more question. Are multi-port external surge protectors considered effective solutions?
Yeah, kind of the same answer.
Yeah, so I guess that's, again, that's kind of a macro system where you're looking at instead of an HDMI cable, you're talking about power distribution system, right? And do the MOVs and things like that in that type of network. Does it clamp the transients that you're going to see? And again, it's the same kind of characterization. You're trying to dissipate and direct. That's another thing that you need to think about, is what is your return path, and Greg alluded to that. And one thing is, it doesn't matter how good your clamp is, if you're trying to funnel that energy back into a return path that's very high impedance, then you're just going to get a high voltage glitch across that. So it's kind of it's a system level analysis that you have to do to put yourself in the mindset of, okay, here's the pulse coming in, here's the shape of that pulse and the intensity of that pulse, where does it go, and what residual elements of that pulse enter the circuitry I'm trying to protect. So it's again, the same analysis all the time.
Great. All right, I think that's all the time we have for questions today. Thank you, everybody, for attending.